Why gravity proves there are no advanced civilizations watching us. You already know the answer to the Fermi paradox. You just don't know that you know it yet. And the reason you don't is that the answer comes from the wrong direction. Not from radio telescopes pointed at the sky, not from the search for biosignatures in distant atmospheres, not from mathematical modeling of civilizational timescales, but from a force so familiar you stop noticing it around age 4, which is also approximately when you stopped asking the questions that would have led you here faster than any telescope ever could. There is a number called the Hubble tension. It is a disagreement, small, roughly 9%, between two independently verified measurements of how fast the universe is expanding. One comes from observing the early universe, the faint afterglow of the Big Bang. The other comes from tracking nearby galaxies using a specific class of stars whose brightness oscillates in a way that tells you precisely how far away they are. Both measurements are careful. Both have been checked and rechecked by people who would very much like to be the one who found the error. Nobody has found the error. The two numbers keep disagreeing, and that disagreement has been getting harder to dismiss with each additional year of data. Most cosmologists will tell you, if you ask them directly, that this is probably a systematic error hiding somewhere in one of the measurement pipelines. They say this calmly because cosmologists have trained themselves not to get visibly excited about anomalies until those anomalies have survived several rounds of independent scrutiny. What they say less calmly in smaller rooms at the end of conferences is that if it is not a systematic error, if the disagreement is real, the implications include things for which we do not yet have good frameworks. One of those implications is the one I want to talk about. It is not the one that appears in popular summaries. It lives 2 steps further in, past the point where most discussions stop because the territory becomes genuinely uncertain. And genuine uncertainty is harder to write about than confident mystery. I want to be honest about where I came into this and what I got wrong before I got anything right. I was not looking for a solution to the Fermi paradox. I was reading about gravitational wave astronomy, specifically about the stochastic gravitational wave background, a low-frequency hum permeating all of space. First detected by pulsar timing arrays in 2023. And I was reading about what we were not detecting that our models said we should be. There are predicted contributions to that background from cosmic strings, from phase transitions in the early universe, from the mergers of supermassive black holes across cosmic time. Some contributions are present, some are not. And the specific shape of what is absent, not just the absence itself, but the particular frequency profile of the gap, struck me as strange in a way I couldn't immediately articulate. I made a connection. It felt almost embarrassingly obvious, the kind of connection that must already be in the literature, written up properly by someone who knows more than you do. So I didn't write it down for about 2 weeks. I kept reading. I went sideways into literature on Dyson spheres, on the Kardashev scale, on thermodynamic constraints, on energy use, at civilizational scales. And somewhere in that reading, I realized the connection I had made was not in the literature, not stated directly, not in the form I was seeing it. The angle I had stumbled into opened a version of the Fermi paradox that was, I became increasingly convinced, considerably harder and considerably more interesting than the version most people spend their time on. What stopped me, the specific thing that made me put down everything else, was a question that seemed almost too simple to be the thing nobody had answered cleanly. If we assume the electromagnetic silence we've observed is genuinely meaningful, what does physics predict we should see in the gravitational domain if advanced civilizations existed? Not what might we see. What must we see given what we know about energy, mass, and the way large-scale organization of matter curves space-time? And then the harder version, what does the specific shape of what we don't see tell us, not just about whether they exist, but about what happened to them if they did? I am still not sure I have answered it. I have gotten closer, I think, but closer to a hard question is not the same as close. Here is the shape of what I want to cover, because the argument tracks better if you know the frame before you know the content. The standard account says the universe is old enough and large enough that advanced civilizations should exist. And if they exist at the scale we'd expect, we should have found evidence of them by now. We haven't. This is the Fermi paradox, and it is a real scientific problem, not a philosophical curiosity. The standard account is not wrong. It is incomplete in a specific direction. What the physics actually shows is something that contains the standard account the way a larger shape contains a smaller one. The silence we've noticed is electromagnetic radio light signals. But there is a second kind of silence that we have only recently developed instruments sensitive enough to hear: gravitational silence. And those two silences have different implications, different structures, different things they can and cannot tell you about what's out there. The piece almost nobody discusses is what a civilization advanced enough to be detectable would necessarily do to the gravitational structure of its local environment, and what the fact that we don't see those signatures means, not just for whether they exist, but for when they disappeared, and at what stage of development. That boundary is not arbitrary, it is set by physics, and it is closer than you might expect. Gravitational lensing will matter to the third piece. I'll define it properly when we get there. For now, let the phrase sit. One note about the second piece before we move. The argument from gravitational absence behaves differently from the first and third pieces. It is not a cause of anything. I included it because its absence matters more than any positive evidence does. A shaped absence is not the same as nothing. It is a message written in a language we are only beginning to learn to read. The Fermi paradox, stated precisely, is not a question about whether alien life exists. It is a question about timescales. The universe is approximately 13.8 billion years old. Life appeared on Earth within the first billion years of its existence, which suggests tentatively, from a sample size of 1, that life is not extraordinarily improbable given the right conditions. The galaxy contains somewhere between 200 and 400 billion stars. A conservative estimate of the fraction with planets in habitable zones yields numbers in the billions. If even a small fraction of those produced technological civilization, the galaxy should be full of them, and many should be far older than ours. The problem is not that we haven't found them yet. The problem is that we should have been found. A civilization expanding at even 1% of the speed of light for 1 million years, a number that is less than 1/10,000th of the age of the galaxy, would have colonized the entire Milky Way several times over. The galaxy should be saturated. It is not. That is the paradox. The standard responses divide roughly into 3 camps. The first says civilizations are there but not communicating by choice or by difficulty. The second says something, the great filter, eliminates almost all civilizations before they reach interstellar detectability. And that filter is either behind us or ahead of us. The latter being the version that should keep you awake at night. The third says the question is malformed, that our probability intuitions break down at cosmic scales. All 3 camps are arguing about electromagnetic detectability, signals, transmission, the kind of presence that requires intention, a civilization choosing to be visible or failing to choose to be invisible. And this is where I think the debate has been conducted in the wrong domain, because there is a form of detectability that requires no intention at all. A form written into the physics itself, unavoidable for any civilization that reaches a certain scale of physical organization. Gravity, mass curves space-time. This is not a metaphor. It is the content of general relativity, one of the 2 most precisely verified theories in the history of science. Any object with mass, a planet, a star, a Dyson sphere, a fleet of structures massing in aggregate at planetary scales, curves the space-time around it. That curvature is, in principle, detectable. And it is detectable regardless of whether the civilization producing it wants to be detected. There is no way to build at scale and remain gravitationally invisible. The physics does not allow an opt-out. The person who first worked through the quantitative implications of this for the Fermi paradox came to it almost by accident. She had spent most of her career in fluid dynamics, working on turbulent flows in systems with long-range correlations, and found her way into gravitational wave astronomy through a collaborator who needed someone capable of handling the statistical analysis of correlated noise. She has said in the one extended interview I found that she considered the Fermi paradox uninteresting for most of her career. A question that couldn't be made precise. What changed her mind was realizing you could ask it about gravity instead of light. That the gravitational version was precise in a way the electromagnetic version was not. And that it had an answer, or the shape of an answer, that the electromagnetic version had never been able to produce. She was apparently a mediocre chess player despite being exceptional at almost every other game involving long-range strategic thinking. I don't know why I find that detail clarifying. I just do. Her central argument goes like this. A civilization at Kardashev Type 2, one that has harnessed the total energy output of its parent star, would necessarily have rearranged enough mass in its local stellar system to produce measurable gravitational effects on passing light. Not large effects, not visible to early telescopes, but visible in principle to the gravitational lensing surveys we have been conducting for the last 2 decades. Effects that appear as subtle anomalies in the way background objects are distorted by the gravity of intervening regions of space. Gravitational lensing is what happens when mass bends space-time enough that light traveling through that region follows a curved path. We use it to map dark matter. We use it to see galaxies behind other galaxies. We use it in the most sensitive modern surveys to look for statistical anomalies in lensing patterns across large areas of sky. Places where space is slightly more curved than the distribution of visible matter can account for. We have those surveys. We have examined the gravitational lensing signatures of thousands of star systems in our galactic neighborhood. We have looked at the large-scale gravitational structure of distant galaxy clusters. We have begun analyzing the stochastic gravitational wave background for the kinds of correlated signals that massive engineered structures would produce as they move through space. We have found nothing that cleanly fits. Let me catch myself there because I just implied something stronger than I can support. We have found nothing that cleanly fits in the regions we have examined with sufficient precision to make the absence meaningful. That is narrower, and the difference matters. Our surveys cover several thousand star systems nearby, plus statistical samples of distant galaxies. It is not a complete survey. What I can say precisely is this. In the regions where we have looked with sufficient sensitivity, the probability of finding what a Type 2 civilization would produce, given our models, and finding nothing, is somewhere below 5% if such civilizations are uniformly distributed through the galaxy. The absence has a shape, and a shaped absence is not nothing. Some anomalies do exist. A small fraction of the lensing data contains clustering patterns that are difficult to generate from dark matter distributions alone. Dark matter follows gravity. It does not concentrate itself into configurations that deviate from gravitational equilibrium. Engineered structures do. Roughly 80% of the anomalies have conventional explanations. The other 20% has a specific shape that the standard frameworks predict shouldn't exist. And a shaped anomaly that your framework says shouldn't be there is historically where physics has found its most important questions. Now, here is the part that will feel for about 4 seconds like a resolution. The reason we may not see clear gravitational signatures of advanced civilizations is not necessarily that they don't exist. It is that we may be looking for the wrong kind of signature. We have been looking for signatures of construction, the gravitational imprint of things being built and maintained. But there is a different signature entirely. The signature of decay, the gravitational remnant of structures that were built, expanded to enormous scales, and then collapsed or were abandoned over time scales long enough that what we observe now is not the structure but the echo. The way a sound persists in a large stone room after the source has gone silent, not the note, the reverberation. What we have, the Hubble tension, the anomalous lensing clustering, the specific frequency profile of the unexplained component of the gravitational wave background might be exactly those reverberations. The gravitational memory of things that used to be organized, relaxing back into the geometry of space at a rate set by the timescales of gravitational physics, which are very long. Long enough that a structure collapsing 1 billion years ago might still be producing detectable ripples in space-time today. Might 4 seconds. Now the floor drops. You are probably expecting this to start wrapping up. I thought so too at this point in the research. The shape of the argument feels like it should be pointing toward landing. It is not. The next piece is the one everything before it was preparing you for. And it is the one I have not found a clean resolution to in any framework I have examined. If what we are detecting are gravitational echoes of structures that existed and then collapsed, the question is not whether advanced civilizations existed. The question is what happened to them, at what stage, and why the timing, if we can infer it from the relaxation timescales of the signals, appears to cluster around a specific threshold of civilizational development. The standard Fermi paradox allows for the great filter to be ahead of us. This is the terrifying option, but it leaves the shape of the future open. We don't know what the filter is. Maybe it's something we can learn to navigate. The electromagnetic version cannot tell you when the filter operates, only that it operates somewhere in the sequence from simple chemistry to interstellar civilization. The gravitational version can tell you more. If the echoes are real and if their relaxation timescales are what they appear to be, the structures that produced them were massive enough to be gravitationally significant at interstellar distances. The civilizations that built them had already passed every filter that operates below Kardashev type 2, the origin of life filter, the emergence of intelligence filter, the development of technology filter. They had passed all of those and reached stellar scale engineering, and then they disappeared. Not before, after. This is a different kind of problem. It points the filter not with certainty, not with anything approaching proof, but with the specific weight of a shaped absence that keeps not going away. It points the filter at exactly the stage we are approaching. The stage at which a civilization's physical footprint becomes, for the first time, detectable at interstellar distances. This is a little like, and the analogy breaks here, which is actually the point like discovering that every climber who attempted a particular mountain returned safely from every elevation below the summit ridge and then disappeared specifically in the final window, not randomly distributed across the climb, specifically there. The analogy breaks because in the gravitational version, there is no external agent, no trap, nothing on the other side. The filter may be a property of what large-scale expansion does to a civilization's relationship with the physics of its own environment. Something that happens not because of anything outside, but because of the internal dynamics of a system that has grown large enough to interact with itself at scales it wasn't designed to navigate. You might be thinking this only applies to civilizations that chose large-scale physical construction, that a sufficiently advanced civilization might find ways to expand without gravitational footprint. If so, you are right to think that, but it doesn't rescue the original question in the way you might hope. A civilization capable of gravitationally invisible expansion has already solved problems we cannot currently approach, which means it passed through a transitional stage where the footprint would have been unavoidable. And we see no signatures of that transition. Not the end state, not the transitional signatures of a civilization moving from gravitationally visible to gravitationally quiet. Only the silence on the other side of a threshold we haven't crossed yet. What does this look like from one level up? The question becomes, what is it about the physics of sufficiently large-scale self-organization that produces consistent disappearance? And from that elevation, the question looks less like an astronomy problem and more like a thermodynamics problem, which is uncomfortable in a different way because thermodynamics has answers. They are structural, not probabilistic. They follow from the way energy and entropy behave at scale. If the answer to the Fermi paradox is thermodynamic rather than biological or sociological, the filter is not contingent. It does not depend on choices, values, or wisdom. It follows from the physics of what it means to be a civilization of a certain size. That is the version I cannot close. I have read the thermodynamic arguments carefully. I understand the framework well enough to see why it might apply. I do not understand it well enough to say with confidence that it does, and I am suspicious of anyone who claims to. There is a calculation at the center of all of this. It involves the ratio between two thresholds. The first is the energy scale at which a civilization becomes gravitationally detectable at interstellar distances. The second is the energy scale at which a civilization's interaction with its own gravitational environment becomes irreversible. The point past which, if the models are right, the dynamics of large-scale organization cannot be corrected without resources exceeding those available to the civilization doing the correcting. The ratio between those thresholds in every framework I have examined is less than an order of magnitude. In some models, considerably less. The window between becoming gravitationally visible and reaching potential irreversibility is, on civilizational timescales, not large. We became electromagnetically detectable approximately 100 years ago. We are not yet gravitationally significant. The two thresholds, if the models are right, are not far apart. So I am back where I started. That number, the 9% disagreement in how fast the universe is expanding, the one most cosmologists still attribute to measurement error. I understand it differently now than I did when I first encountered it. Not better, exactly. Differently. It might be nothing. It might be the residual gravitational signature of something very large that used to be organized, still reverberating through the curvature of space at a frequency set by timescales we can barely imagine. Relaxing slowly back into a universe that does not keep records of what it used to contain. The question has gotten cleaner the further in I've gone. The discomfort has gotten considerably worse. That is usually what happens when you follow something far enough. The question sharpens. The ground gets softer. I think that's the honest place to stop for now.